Okay, now in the last part of this lecture, I'm going to tell you how we can use path limits to show that a given limit of a function of two variables does not exist. All right. So what are these limits along different paths? So basically, it is probably better to think of a path as a curve um, on the plane xy, right? So imagine that we don't really care about the graph of our function, so we only look at the plane xy, right? So and this is what it looks like. So we have the plane xy, and we have some point AB, and then the idea here is that it is probably a bit hard to compute limits as xy approaches AB, but maybe it is not so hard to take some path that passes through the point AB and take the limit of our function along this path. Because essentially a path is something one-dimensional, and something one-dimensional essentially means that there is just one independent variable. So, and then by computing limit along a path, we essentially do computation of a limit of a one variable function. So let me show you how it works on some examples, right? So suppose that we want to compute this limit, right? So this is the limit. Um, Now, the good idea is probably to do a little bit of visualization of the plane xy, right? So this is the plane xy. Um, this is the point 1, 0 to which xy is supposed to approach. Okay, our first path is um, so let me do this. So the first path is x equals 0, right? So x equals 0 is our path, and this is what it looks like. It's just the y-axis. And of course, it doesn't really make sense to take the limit along this path because it the given point, 1, 0, is not on the path. So which it essentially means that it is not a valid path. Okay, so the first attempt didn't work. Okay, so let us try some other paths. So let me again draw my xy plane, and this is my point 1, 0. So instead of using this path that doesn't work, so let me try two paths that do work. So one of them is going to be this vertical line, x equals 1, and one more is going to be the horizontal line, which is y equals 0. Okay, so let me do the limits along the paths x equals 1 and y equals 0. Right? So the limit of my function x square minus x minus y square divided by x minus 1 plus y square as xy goes to 1, 0 along the path y equals 0. So if we take the limit along the path y equals 0, essentially it means that we need to replace y with its value, with 0, right? So this is going to be just the limit of, now y becomes 0. So x squared minus x minus 0 squared divided by x minus 1 plus 0 squared. I mean, of course, I don't have to write 0 squared, so I can just erase it. And now xy approaches 1, 0, but now y has been accounted for, so the remaining variable is x, and x approaches 1. So I've got to compute this limit, and I can do it. So this is the limit as x approaches 1. Now I'm going to rewrite x squared minus x as I'm going to factor out x times x minus 1 divided by x minus 1. So cancels out. So this is the limit of essentially of x as x goes to 1, and this is 1. All right. So what we see here is that the limit of my function along the path y equals 0 is 1. So this is 1. Okay, so let me try, well, in the same way, I'm going to find the limit of the same function at the same point, but along the path. So xy tends to 1, 0. But now I'm going to look at the other path at x equals 1, along the path x equals 1. Right? So essentially it means that now I'm taking the limit. So x has been accounted for now. So, but now y approaches uh, 0 instead. And x is 1. So this is going to be 1 squared minus 1 minus y squared divided by 1 minus 1 plus y squared. Well, of course, as you can see, 1 squared cancels out, this cancels out, so the remaining part is the limit as y goes to 0, minus square over plus minus y squared over y squared is just negative 1. And this is negative 1. Right? So what we see here is that there are two different limits on two different paths. So which means that the limit of the function of two variables does not exist. Right? So here is the first limit, here is the second limit. Now, hypothetically, I mean, if you wanted to really explore different paths, you could actually compute the limit along any path. Like if this is your point, so your plane xy, right? So the point 1, 0. Instead of the limits along straight lines, you could even compute limits along circles or parabola or whatever. I mean, so for example, you could take this parabola y equals x minus 1 squared. Um, this is also a path that contains the given point, right? Maybe just for your information, I'm going to show you what it looks like on a surface. So if you plot the graph of the function of two variables, this is what it looks like. I did it for you. X squared minus x minus y squared in the wait a second. So there is yeah, this is what it looks like, and here is, you know, I mean, it kind of sounds, well, looks a little bit strange, this surface, but you do see that there is kind of a gap here or a crease here that indicates that there's not going to be a limit at the given point. Well, at the same time, so the limit along the path x equals 1. So I believe that x equals 1 is probably, well, I guess it is a bit hard to see. Okay, so the red axis is x, right? So x is 1 is, I guess, this line. Well, and y equals 0 is probably the other line, this line, and you probably can kind of see that the limit along the line y equals 0 is 1, and the limit along the line x equals 1 is negative 1. Should be able to see, but again, it takes some effort to figure out what's going on. But what is immediately clear here is that because of the shape of the graph, you see that in the middle here, that there is no limit. Okay, so these path limits are used to verify that the limit does not exist, right? So basically, if any one of path limits does not exist, or if you found two path limits and they're different, so they both exist but they're different numbers, then the limit of the function of two variables does not exist. Okay, so now maybe a little question for you to think about is, suppose that you computed limits along two different paths, so like, I don't know, along x equals 0 and y equals 0 or something like that. Can you conclude that the overall limit exists or not? Okay, and I'll give you a hint. In order to figure it out, you probably need to consider something like the familiar function xy divided by x squared plus y squared. It'll do the job. Well, anyway, so let me continue. So here is another specific example. does this limit exist? Oh, sorry, it's the same example as before, right? So does this limit exist? And well, as I already mentioned, so since there are two different paths and limits along two different paths are different, it means that the overall limit does not exist. Okay, so here is a different example. So here we have a function that is defined in a somewhat strange manner. It is a piecewise function. So if xy is not zero, its value is is given by the given formula, and at 0, 0, its value is by definition zero, right? Okay. So the question is, does the limit exist, and whether the function is continuous? Now, again, so to solve this, what we could do is maybe first think a little bit about how we can approach it. So I find it useful to do this little sketch x y. So the point, so our limit is at as xy goes to 0, 0. So the interesting point that we are looking at is the origin. So what could possibly be two different paths? Um, that contain the origin. I think the easiest, kind of the most obvious paths that we can think of are, y equals 0 and x equals 0. So x equals 0 and y equals 0 are two paths, right? So I'm going to compute the limit of this given function, 2x squared minus y squared over x squared plus y squared, as x, y approaches 0, 0. First, along the path, um, x equals 0, and second, along the path, y equals 0. Okay, so first, when x equals 0. So along the path x equals 0, essentially it means that I replace x with 0. So then I get, replacing x with 0, I get minus y squared in the numerator and y squared in the denominator, right? And this is negative 1. So which approaches negative 1 as x, sorry, x is already 0, so as y goes to 0, as y goes to 0. Okay, so the limit along the path x equals 0 is negative 1. So what is the limit along the path y equals 0? So when y equals 0, essentially it means that we substitute 0 for y, and the remaining part is 2x squared over x squared, which is 2. And of course it approaches 2 as um, as x goes to 0, right? So the limit on the second path is different, is 2, right? So what we see here is that one of the limits is 2 and the second limit is negative 1. Okay, so the limit along the path y equals 0 is 2. The limit along the path, okay, so in my notes I have another limit, so as x, so along the path x equals y. Okay, so maybe it's just another way to solve it. So I think it's good to know both ways. So one is to use the x equals 0. The other one is to use the limit x equals y. Right. So if we take the limit along the path x equals y, it essentially means that we just replace x with, well, y with x in the given expression and let x approach 0. Right. So this is what we get. And there is an error here, so it should be 1/2, of course, not 1. I will fix it in the notes. But still, the important thing is that the result is different from, so the limit along the second path is different from the limit along the first path. Okay, so since the limits along two different paths are different, we conclude that the overall limit does not exist. Now, what can we say about whether the function is continuous. So, and notice that the definition of continuity is that the limit of g of xy as xy approaches 0, 0 should be equal to g of 0, 0, which here we're given to that g of 0, 0 is 0, right? So, and the question is, so is this correct? So, is this correct? And the answer is that this is not correct, because the limit is just simply undefined, right? So, and for a function to be continuous at a given point, so it must have a certain finite value, and the limit of the function must be equal to that finite value. So if the limit does not exist or undefined, it just means that the function is not continuous, right? So this function is discontinuous at the given point. Okay, so now this is the end of the lecture, and here is the last quiz for you.